Alright, my name is Josh Holland, and my project was the topology optimization of a joined aircraft wing structure. Joined aircraft wing is an unconventional design where lift is distributed between two wings connected in diamond configuration. Aircraft designers primarily use a cantilever configuration for aircraft wing structures, and the joined wing configuration offers distinct advantages over the conventional cantilever design. Specifically, it reduces the induced drag wingtip vortices on the wings from an almost doubling effect of the joined wings aspect ratio compared to a cantilever wing. There are also advantages for the joined wing design because the aft wing is a structural brace for the front wing, which allows lightening of the front wing structure. This is an important optimization problem because joined wings have the potential to dramatically improve the efficiency of aircraft, specifically long-range and transport aircraft. This is an optimization problem because the design trade-offs and effects produced from varying configuration parameters such as structural mass and volume. These are just pictures of a conventional cantilever wing structural design, which is also called a wing box. The structure has forward and aft spars, rings, ribs, and top and bottom skins, and typically the volume between the ribs and the skins are used for fuel storage. The first joined wing configuration was proposed and analyzed in 1967 by Wolkowicz. Gallman and Crow also contributed a significant amount of work to analyze and optimize the joined wing. Specifically, they verified the structural weight savings by performing a joined wing structural optimization, determining the optimal wing joint location at 60% of the span of the front wing using nonlinear optimization methods. For this project, an airfoil shape optimization was also completed, which minimized airfoil drag and maximized volume. The analysis was completed using a MATLAB program I found on MathWorks website. It used a symmetric airfoil as an input, and it runs through an airfoil parametric analysis to determine its performance, and then uses a conjugate gradient method to optimize the airfoil shape. The goal of the optimization project is to produce a joined wing design that minimizes weight and maximizes volume. The system boundaries taken into consideration are the joint where the forward and aft wings meet, which is fixed at 50% of the span of the forward wing. This was determined based on the analysis completed by Gallman. The upper bound for the optimization is a maximum volume fraction of 0.1. There will be 4 base cases to start the optimization runs, with 3 specific models for each of the base cases. 3 models for 3 of the base cases, and 1 base case reuses 1 model. The specific space for this optimization problem is a continuous search space, and optimization problem. The optimization problem uses a deterministic search technique through HyperWorks optimization toolbox. The approach used to solve this problem was broken down into 3 steps. The first step is to optimize the airfoil shape, which is completed using the MATLAB program that I mentioned. The second step is to complete a high-level loads analysis for the wing for drag and lift produced, also using MATLAB program. And finally, a topology optimization is completed for the forward wing using HyperWorks. So optimization will use 3 wing box designs. Here's the results of the airfoil optimization, which again was started with a NACA 0012 symmetric airfoil. The lower right corner shows the optimization runs for this specific design, the gold airfoil being the optimized design. Specifically, this program will minimize the drag, and then it's subject to pitching moment, lift coefficient parameters, and Reynolds number parameters. Loads analysis was completed using a vortex lattice method code in MATLAB. The resultant load was a total lift of 9,000 pounds for the aircraft and 300 pounds for the front wing of drag. The optimization model in HyperWorks minimizes the weight to volume ratio with the parameters listed. Specifically, the parameters used for optimization are the volume fraction upper bound of 0.1 and compliance. The model for base case 1 is shown here, which is a solid aluminum beam swept at 18 degrees aft. The lift, drag, and moment loads are applied to the tip of the wing, and the wing joint is constrained at 50% of the span of the front wing to simulate the aft wing. The model base case 2 uses the same solid beam for base case 1 with lightning holes drilled from the root to the tip of the wing box, as shown. The lightning holes are a common feature for aircraft ribs. The model for base cases 3 and 4 again are modifications of base case 1. Base case 1 is modified here to adhere to the design which is more similar to conventional cantilever wing with ribs, spars, and skins, as can be seen. The results of the optimization for base case 1 are shown here. The output results show an element mass of approximately 6.8 times 10 to the negative fifth, which is the mass for the elements of the structure. To determine the mass for the entire structure, this number is multiplied by the number of elements in the model. The calculated mass for the design is approximately 342 pounds. The objective function is a result of the mass to volume ratio, which should be a minimum for the design, converging to a minimum feasible design with all constraints satisfied at iteration 28. And also the picture shows the optimized topology for this base case. Here the topology results again are shown with the video of the evolution for each iteration. Base case 2, the results of the optimization for base case 2 are shown here. This produced a total mass of approximately 587 pounds, and the plot shows the objective function converging on a minimum feasible design with all constraints satisfied at iteration 28. This element mass is more than base case 1, and the objective function produces a less favorable mass to volume ratio, so base case 1 is the optimal design so far. And this is the animation of the iterations for the design topology optimization. Shown here are the results for base case 3. This produces a total mass of approximately 389 pounds for the structure. The mesh for this size was also ran at about half of the mesh size of the previous 2 runs because the complexity of this model for the wing box shape, specifically the ribs and the cutouts in the model, made the meshing a little more difficult. The plot shows the objective function converging on a minimum feasible design with all constraints satisfied at iteration 23. And the element mass is slightly more in this base case, but the objective function produces a more favorable mass to volume ratio, so that makes base case 3 our optimal design so far. And here's an animation of the iterations of the topology design for base case 3. So shown here are the results for base case 4, which is actually cantilever wing with the same design parameters and model as base case 3. The only fixed point on this model is the root of the wing box. There is no wing joint simulated here. This produced a total mass of approximately 3,900 pounds for this structure, which is significantly more than the previous ones. The mesh for base case 3 and for this base case was reused from base case 3. And the plot shows the objective function converging on a minimum and feasible design with all constraints satisfied at iteration 23. This element mass is more than base case 1, and the objective function produces a less favorable mass to volume ratio, so base case 3 is our final optimal design for this project. And here's the animation for base case 4 design evolution through each iteration for the topology optimization. So in summary, the final optimized design is shown here, which turned out to be base case 3. And this produced the minimum objective function and one of the lowest masses for the wing box, which is a feasible design. There's still a good amount of work that needs to be continued for the joint aircraft wing optimization. Some of the focus areas for this work could include adding more fidelity to these models, specifically the ones used in this project, with finer mesh sizes and different starting base case models. The optimization problem should be reran with load distributions which are more close to real-world representation, such as pressure distributions on the wing surfaces, whereas I just use point loads at the wingtips. Also, more detailed constraints for the problem should produce more real-world representative results. It would also be beneficial to use a discrete search space based on industry material sizes for the skins and the ribs. This could produce a more realistic design.